No, I think I'm just going to introduce Rafal and then take it away. All right, welcome everyone for our joint seminar series on innovations in transportation. We'll hear from various speakers talking about CAVs, generative AI, future of transit. Our first speaker is Dr. Rafal Stern, and he studies mixed autonomy traffic flow and data-driven strategies. He has his bachelor's, master's, and PhD from University of Illinois, Urbana-Champaign, and was at Technical University of Munich for his postdoctoral work. His talk will kind of talk about emergent traffic behavior and flow efficiency elements. And yeah, look forward to hearing.
Thank you so much. We've been just really impressed with come on in with sort of every aspect of this visit. So a huge thank you to you for hosting us and for putting this all together. Very generous of you all to give us 4 one-hour slots to talk. I really appreciate it. I'm going to try to be on time because I know I'm not going to hear the end of it if I'm not on time for my colleagues. So I want to talk today about some work that I'm doing, looking at sort of mixed autonomy traffic. What's the impact of automated vehicles? I'm a transportation engineer. I come at this from the transportation of the civil engineering side. So I look at this in terms of the impact of the infrastructure. At the end of the day, there's a lot of different ways in which vehicle automation might totally change how we think about transportation. We'll hear a little bit about it from Ali Reza with some real impacts on transit possibilities, but also sort of perhaps more driving because you're reducing the cost. Regardless of how that pans out, as civil engineers, we're sort of dealt that hand, and then we have to come up with a way to make the infrastructure that we have match it. And a large part of this is sort of, ideally, hopefully the answer isn't we have to rethink all of our infrastructure because we've spent billions of dollars building it. And it would be really a shame if the answer is we need to totally change it. So the hope is that we have some sort of way to adapt our current infrastructure and make it sort of forward compatible for an autonomous future. Just a real quick sort of housekeeping item here. Should I turn it? Okay, I will start my video. I'm not convinced that it will be the best shot of me. It'll be, but I will. There we go. Okay, so I'm not going to unmute myself though, right? Because I'm going to say later. Sorry, I'm getting a lot of prompts here. Okay, so the big question that I'm interested in is how will increased vehicle autonomy impact traffic flow? And then there's sort of that follow-up question of, okay, something's going to be different. What does that mean from a civil engineering perspective for our transportation infrastructure management? And one of the things that I personally get really excited about and really interested in is traffic jams. People generally hate them. I hate being in them. Remember, you are not in traffic. You are part of traffic, right? But I find them really interesting as sort of a mathematical phenomenon. And specifically at the top here, this is the type of traffic jam that isn't really caused by any sort of infrastructure-related bottleneck, right? There's a lot of good reasons for traffic. You might have construction, reduction in capacity. But these are traffic jams here that aren't caused for any sort of like infrastructure-related bottleneck, but instead they're the result of, well, of human driving behavior. This was sort of shown famously in 2008 for the first time by these researchers in Japan, who said, let's get rid of all of the externalities of traffic. Just look at pure, people driving behind other people, and look at what that means for traffic flow. And it turns out that if you get a ring of traffic, you can get pure car following, basically only people driving behind other people, and you get really nice, you still get this, you start with traffic, and you relatively quickly get this traffic wave. It turns out that they didn't just get lucky. I've done this experiment a bunch of times, and without fail, every single time you do it, you're going to get traffic. Okay, so what's actually going on here? These what we call phantom traffic jams. It's really the result of a property of traffic flow that we call string stability. And specifically, string stability is sort of what happens. Imagine a string or a platoon of vehicles, group of vehicles driving. They're all driving at the same speed, same spacing, and then the vehicle in front hits the brakes. And the question of string stability is, what happens to that braking event? Do subsequent vehicles have to brake more and more? In the case of string unstable traffic, and until you get maybe a full-blown stop and go wave, or do subsequent vehicles brake less and less in the case of string stable traffic? And as we've seen sort of in that experiment in Japan, as well as in a number of other experiments, including some recent data collected in the southeast here and outside of Nashville, Tennessee, this is 4 different lanes of highway traffic on I-24. These things, human drivers are string unstable. These things are going to arise, and they're going to cause disruptions to the. Okay, so my question several years ago, sort of at the very end of my PhD, was what happens when we start to see autonomy? What happens if, I'd love to have fully automated, fully connected vehicles, but in the interim, before that happens, what if we swap out a small number of those vehicles for automated vehicles? Can we drive them better? And can we drive them better in such a way as to get rid of some of that congestion? But I'm going to skip, 4 years, 3 years of math and just show you the result. And that is this video here that shows where we did exactly that. So what you see here is that same ring road setup, 22 cars. The vehicle with the arrow on top of it is autonomous capable. It's currently being driven by a graduate student who's driving. You see the speeds at the bottom, and you'll see relatively quickly stop and go waves emerge. 22 human drivers. At this point, what we do is we hand the control over on that one vehicle to an automated controller. And so now the autonomous vehicle is taken over, and it's driving a little differently, and it's driving a little better. And the nice thing is it's able to totally smooth out those traffic lanes. To be clear, the other 21 people on that ring had no idea what was going on. We paid them. We told them, show up, we'll pay you to drive in a circle. That's all we told them. They don't know there's an autonomous vehicle. They don't realize what's going on. But that one vehicle driving differently, one vehicle changing its driving behavior, changes the dynamics of the whole problem. And that's kind of the premise of what a lot of my concerns and a lot of my hope is resting on. Okay, so you can see pretty clearly here, these are space-time diagrams, like traffic engineers love these, time on the horizontal axis, position on the vertical axis. You can see where those traffic waves emerge, and as soon as you activate autonomy, the traffic smooths out. Okay, so now that is like a very purpose-built, designed, autonomous vehicle, test vehicle, that's designed with a controller that is intended to dampen these traffic waves. The question is, what happens with, there's a lot of different types of autonomy and different levels of autonomy. Sure, many of you are familiar with this, but you start at level 0, what many of us or I drive. That's not an autonomous vehicle, and you look at who's in charge of the vehicle, that's always the human driver. But as you introduce sort of level 1 driver assistance, level 2 automation, what you're doing is you're taking some of those autonomous driving capabilities and you're handing, or some of the driving tasks, and you're handing them over to the vehicle. As you go to higher and higher levels of autonomy, you're basically just taking more of those tasks and handing them over to the driver or to the vehicle in more and more contexts or more and more situations. And while full autonomy that solves our congestion problems might be a ways away, turns out that we have a lot of vehicles already on the road today. As anecdotally, the rental car I picked up to drive here from Raleigh, Durham, has adaptive cruise control. I drove it last night, right? What is that doing? That's taking some of those driving tasks from the human driver, handing them over to the automated or to the vehicle. We just said that doing that has the potential, depending on how those things are programmed, has the potential to totally change the way the traffic behaves. Might have implications for things like throughput, as we saw. Now, if you look at the literature and say, are these adaptive cruise controllers or ACC string stable? Look at literature from the early 90s, pretty resounding yes. Easy to build them to be string stable. Okay, so solve problem. Not quite. Turns out when you rent one, or if you have one that you drive one and you observe it, you will see that it perhaps isn't actually string stable. This is what I noticed a couple of years ago. So I decided to rent a whole bunch of different ones and test them. You put a GPS receiver on the front, on one car in front, that's your lead vehicle, GPS receiver on an adaptive cruise control vehicle in the back. You drive both of them. The back vehicle has ACC on. The front vehicle speeds up, slows down just a little bit, and you see how the following vehicle reacts. And if you look at the data, it turns out that, well, it starts to overshoot a little. In fact, we did this with sort of a platoon of 7 ACC vehicles. The front vehicle hits the brakes a tiny bit, and by the time you get to the 7th vehicle and back, you're slowing down by 30 miles per hour, so much so that this particular make and model said it's no longer safe to drive with ACC on. This is a massive cue that I'm hitting in back, the backup, and I need to hand control back over to the human driver. And so, yes, in theory, you can design them to be string stable, but what the car companies are doing, and to be clear, they're building cars that are safe, that are comfortable, that sell, but they're not building cars with traffic properties in mind. And that's because there's a whole bunch of sort of nonlinearity in the engine, the transmission, everything down to sort of the road tire interface that adds delay and makes it a much harder problem than just a simple plant dynamics. Okay, so then we started with human drivers are unstable. If we have good AVs, they're string stable and can stabilize the flow, but the current AVs that we have I will say not that you guys have, because I've seen much better today, but the current AVs that you'll buy off the lot or that you get off the lot in enterprise, those are string unstable. So what does this mean for traffic flow? Okay, so that's what I sort of want to think about a little bit. We can look at this in simulation. We've spent a lot of time building really nice car following models for different types of vehicles based on that type of leader follower data that we've collected. And we can look in simulation at what happens. So first, if you look at the literature and say what ought autonomous vehicles to behave like in the future, and you model that, what you see is an increase in capacity, right? So if you look at this, this is a fundamental diagram. If you're a traffic engineer, you might have seen this before. You've got sort of flow versus density. The higher the density, the higher the flow, until you hit a critical density at which traffic breakdown occurs, and that's where congestion sets in. And the nice thing about sort of theoretical autonomous vehicles, sort of like we saw in that experiment, the ones that we want but don't quite have yet, they're going to probably mean congestion sets in at higher densities and you get a higher maximum throughput. If you're a traffic engineer, that's awesome. 30% higher throughput, that means your 3-lane highway just became a 4-lane highway and all you did was change the cars that are driving on it. You didn't have to build a single lane mile, right? But if you look at the data from the adaptive cruise control vehicles that we have, you see a different picture. So I'll look at sort of different percentages of cars using adaptive cruise control, and what you see is maybe a 20 or 30% reduction in capacity. So your 3-lane highway just became a 2-lane highway because people turned on their adaptive cruise controller. And all of a sudden, your 3-lane highway that was already nearing capacity is now far above capacity. Okay, so my vision for how we can address that is we need to know who's driving, or the properties of the vehicle driving determine the characteristics of the flow. And the characteristics of the flow are crucial for doing control on that flow. Ramp metering, variable speed limit, etc. And so I envision a world in the future where we look at who's driving. Maybe we do some sort of driving pattern recognition to determine what types of vehicles are driving. We then use that to come up with sort of a fundamental diagram that doesn't just depend on density, but where flow depends on density and market penetration rate of autonomous vehicles, or market penetration rate of adaptive cruise control vehicles. Basically, not just what's the current density, but what type of vehicles are here, what flavor or what variety of vehicles are here, because that ultimately is what determines the flow properties, and that then could be used to update the control. And I have a number of different results sort of along those lines. So that's the big picture vision. There's one more thing that I will say, and that is this goes both ways. So if you imagine a malicious attacker slightly changes the way vehicles drive, you could also play this game maliciously and deteriorate the flow. And the challenge here, this is another area that I've been looking at, the challenge here is an obvious attack is drive the car off the side of the road. But it turns out if all of my car makes, if all vehicles of a certain make and model drive off the road suddenly or crash into other cars, that's really easy to pinpoint. But if all the vehicles of a certain make and model just drive a little bit worse, you could see massive increase in congestion without being able to tell what's going on. And I think that's one of the risks. We've looked at some simulation work that suggests that very minor changes to the vehicle behavior mean relatively large changes to flow, and that could be pretty damaging. So in summary, increased vehicle autonomy is going to change traffic flow dynamics. The short-term trend, likely decreased capacity. The long-term trend, likely increased capacity. Either way, if you're a traffic engineer, you have to deal with that different capacity, which means perhaps changing the way, or like if we know what types of vehicles we have, we can perhaps change the way we do control and customize it to the traffic makeup. Finally, there's this, what I call these stealthy attacks that could happen through some sort of push a malicious software update. And I think while there's very difficult to localize, certainly a lot of room for work in terms of how do we identify these and then how do we combat these. Thank you very much. I really appreciate the opportunity to be here, and I'm going to hand it over to my colleague, Michael, who I believe will present next. Thank you.
Great. Thanks. Yes, that's perfect. Thanks, Rafael. And since, as you'll see, I think there are 4 speakers, so we'll continue on and hold on the questions towards the end. So our next speaker is Dr. Michael Levin. His research focuses on traffic flow and network modeling, and he has his bachelor's in computer science and PhD in civil engineering from University of Texas at Austin. He has served on TRB's network modeling committees, worked on prestigious journals like Part B and IEEE ITS. And Michael has been my grad student colleague since, so I've had the pleasure to know him. Michael, the floor is all yours.
Thanks. Oh, I'm also here.
Oh, you just had it.
I just have it, yeah.
That's great.
Yeah, we're working with 4 Zoom screen shares, so hopefully it works out. Yeah, we have some extra chairs. Thanks.
Yeah, please, there were cheers, so, I'm Michael Levin, I'm, at University of Minnesota, been there, I think this is my 8th year. And so I've been looking at different questions of like, how do you match vehicles to passengers, right? So here's kind of the,
Sorry, is it not working?
right back
You can bring your computer here.
Yeah.
There's 2 chairs here. It's a shame to have these be unused if there are people standing. Please don't be shy. I rarely bite.
All right, so the question I have, is like, we're familiar with Uber and Lyft, transportation network companies, right? And of course, Ali Kramardini is working on the automated shuttles, and we're also, looking at we have different commercial options that are similar to these. So the question I am asking though is, when you pull out your phone and you ask for an Uber and Lyft to pick you up, how do we decide which vehicle gets matched to you? Right? And that's obviously a problem currently with Uber and Lyft. That's additionally a problem if we're looking at Waymo or other shared autonomy vehicles. I just had a chance to take a Waymo in Austin. It was really cool. There's no driver. You just get in and the car drives you to where you want to go. But you end up with a situation where we have a very large fleet of vehicles potentially serving passengers. And so it's a challenging problem to decide which vehicle gets sent to which passenger. Here with Waymo, we might end up with a lot more people using them because you don't have to pay for a driver, so it might be cheaper than trying to call up an Uber and Lyft and paying that driver to drive you around. It may even come cheaper than owning a automated vehicle yourself because those are kind of pricey. So we have these questions like, could these shared automated vehicles be replacing your privately owned vehicle, especially if you're not driving all that much? But then there's still a question of like, how do we, you would not want to get into a Waymo car or an Uber Lyft or something if you have to get out your phone and wait for like 20 minutes before you get picked up, right? So that's kind of the question is like, how do we make sure that we're serving passengers? And here's, where this becomes a very challenging but very interesting mathematical problem. So this is fundamentally, you can, some of you I saw in the posters were formulating integer linear programs. Problems of, you have an optimization problem, you're trying to solve this problem. And you can model the matching of passengers' vehicles as integer variables and as an integer linear program. But that doesn't quite tell the whole story, because if I were to take all the people right now who pull out their phone and request an Uber and try to match vehicles to it, I would be completely ignoring everyone who's going to try to get an Uber in the next 5 minutes, who I don't know about yet, right? And those people, we know they're going to come. We don't know exactly who they are, where they'll show up, where they want to go. So there's stochasticity, there's uncertainty in that. We can predict maybe the averages, but we can't predict them exactly. And so trying to optimize this situation where we want to not only provide service to the current passengers, but also people in the next 5 minutes, the next 10 minutes, that becomes a Markov decision process where we have this stochastic model, and we have optimization decision variables within it. You cannot solve this computationally. There are too many dimensions. What you can do is find a simple mathematical solution algorithm and try to derive some nice performance properties mathematically. So this is why I like this, because there's math, but it's very useful math. Okay, so here's where I'm going to introduce some techniques here. So what we want to do is keep track of the longest waiting time of the customer at any location. So maybe like if all of us in this room got our phones and started requesting Uber whoever's been waiting the longest, that's the person we're going to keep track of. That's the person we're going to serve first. And then the next person in line, that's the person who would serve next, right? And what we want, if you imagine a large group of people with these waiting times, we want those waiting times to be bounded. In other words, we don't want, as we have more passengers, more customers entering the system, we don't want you to wait 10 minutes and the next person waits 20 minutes, next person 30 minutes. You know, we want it to be like, okay, it's on average 10-minute waiting time for everyone. So in other words, if these waiting times on average are unbounded, what we have is some customers are not being served. So the flip side is if we have them being bounded, mathematically saying it's less than infinity, then we are serving everyone at a good rate. And that's what we want. Okay, so how do we get that to happen? So we have a model, and I'm not going to go through all the details of the math. Basically what we're saying is I want to track the change in a waiting time. And that change in a waiting time depends on what if the passenger gets picked up? Okay, then the waiting time goes down because the person who was waiting longest got picked up. Now that person's not waiting anymore. So you track that, and the rest of it's just kind of different cases. All right, so then we have to combine that with the kind of intuitive model of how you match vehicles and passengers. So it would be some variables, right? Let's say, does a specific vehicle get assigned to a specific passenger? If so, then that's going to be what we call 1. If not, then we'll call it 0. And if we add up all these variables, we can tell which passengers are being served and which ones aren't. And so that's what we're trying to optimize, is decide what those should be. Then we end up with this control policy that is a combination of a couple of things that are quite intuitive. So the first thing is we want to minimize vehicle service time. So this is the time that you spend having a vehicle drive around empty to pick people up, right? You don't want to send vehicles to passengers that are far away. You want to send them passengers that are close by. But if you only focus on sending vehicles to people that are close by, what if someone in Raleigh calls up and the only vehicles available are in Greensboro, right? And then, so you've got a very long travel time, and you kind of have a problem there because if you only look at short vehicles that are nearby with short travel times, you're never going to serve that person. So we have to have a combination of vehicle service time with the passengers that are actually being served. And so idea is, as passengers are waiting longer and longer, we start to expand the range of vehicles that we would send there. And then the rest of it is just constraints on where can we send the vehicles. Okay, so this is a simple, kind of intuitive decision. You might be asking, why is this a good idea? That's because mathematically you can prove that this intuitive control algorithm will actually serve all the passengers, if at all possible. And that's kind of nice because if you look at what people are doing to match vehicles and passengers, a lot of time it's very heuristics. It's maybe machine learning, it's maybe solving this optimization problem that only works for the next 1 minute, but doesn't really consider the future at all. And so this is actually considering the future and looking forward, but it's still quite easy to solve. All right, there's some various math on how you implement this. I spent a lot of time working on that, but I don't think that's what we want to talk about here. So here's some results on what this looks like. Well-known test network, you know, that's, I borrowed it because he had some data. Here's the interesting, thank you. Here's the interesting part. So this graph shows time on the x-axis versus the number of passengers that have not been served, number of people in the system. So what we are going to see is, like, if we start off with an empty customer list, it's going to increase, but it's going to level off at some point, and it says, okay, we're serving people. You know, there are always some people waiting, but we're serving people. On the other hand, if it just increases like this, and it keeps increasing over time, it's basically saying, as time goes on, the number of people in a system who are not served, who are waiting for pickup, that's just increasing, and you're ending up, you know, if you're this passenger, you're going to have a very long line of people ahead of you. That would be unhappy. All right, so there's various parameters you can play with, you know, in terms of saying how long do you have to spend being waiting to get picked up. And these are all simple, but you know, modifications to algorithm that keep our performance properties of we're serving everyone. Various results. So we also compared this to some other controls in the literature. This LBHFF, that's a existing algorithm that it's called feed forward fluid control balance collar. The point is, we can do better, especially when we have a small number of vehicles, we can serve more passengers. And we can prove that mathematically, and we can show it in simulation. So the other thing that's really interesting here is you might say, okay, we have some number of people in Greensboro. How many vehicles do we need? Like, Ollie's got 6. How many vehicles do we actually need to serve all the trips? Right? And this actually tells us, because part of the process of proving that we can serve everyone is determining what's the set of passengers that can be served. So we can write down some equations that say, okay, if we have 10 vehicles, this is how many passengers we can serve out. And here's mathematically what that would look like. What we have is some equations that say, okay, the vehicles that go to, say, campus, they have to leave campus at some point. You can't have vehicles appear or disappear there. We have to serve all the customers, that's what we want. And we also look at how much time it takes for each trip. So if on average it takes 10 minutes to pick you up and then 20 minutes to drive you, that's 30 minutes. Now, if we look at one vehicle making a 30-minute trip on average, it can make 2 of those per hour. So we can figure out how much effective service time we have, and that helps us figure out how many vehicles we need. So with this, we could optimize, how many vehicles do we need. If we're looking at, say, electric vehicles that need to recharge, we can say, okay, if we place the charging stations nearby, each vehicle can serve more passengers. But if we place them farther away, it might be cheaper, but we need more vehicles. So we can explore that trade-off mathematically. And here's kind of the optimization problem of saying, like, we want to minimize the cost associated with serving all the customers that we expect to have. So here's some graduate students and undergraduate students who worked with me. Hopefully, it can give you kind of a flavor of trying to solve a real world practical problem with the core mathematics of what this problem exists. And yeah, happy to talk about that more later. That's fine.
Thanks, appreciate that. So again, in the spirit of time, we'll keep the questions towards the end, and we will move on to our next speaker. Okay, hopefully you can share your screen. All right, I think my
feel pressure because
I can
2 speakers have their time. I think I am going to be the one who
I yield the balance of my time.
Okay.
All right, so actually, yeah, why don't I introduce you first? So we have Dr. Sungjin Choi. He's an assistant professor in civil engineering in the University of Minnesota. He focuses on machine learning and generative AI models and working with transportation mobility data. He has, prior to joining University of Minnesota, he was a postdoc at McGill in Canada and graduated from KIST in South Korea. And all his degrees are in civil engineering, and his research we'll learn more about as he talks about this.
Right. Thank you so much for giving me this opportunity to share what I've been doing so far as a researcher. So this is a research topic that I've been working on from my PhD. So it started from my PhD and some work I did from postdoc, and the most recent one on using LLM and VLM for traffic operation. So when we talk about data, essentially we collect the data from real world, and then as a researcher, what we are trying to do is to build a model that represents the world, right? So we are trying to build a representation of the real world based on the data we collect from the real world. So, for example, if we have a traffic, we collect, say, traffic state data, like traffic flow, traffic speed data, or we also collect trajectory data from, for example, NGSIM, and then we develop traffic flow theory and driving behavior model to model it. And we do many things out of it, but one of the things we do is that we build traffic simulator, and then we generate some virtual world that we can simulate things. So essentially, we are generating synthetic data to understand what's happening in the real world. So my definition of data, and I think some of us will agree to this, is that data is a sample from distribution. And as a modeler, what we are doing is to understand this, distribution by modeling the distribution of the world. Okay, and there are many ways to kind of learn the distribution from the data. the most straightforward way is that we assume some kind of distribution. So for example, we are assuming that our data is following some Gaussian distribution or Poisson distribution, and then we might want to fit the parameters associated with those distributions. But one promising and one interesting approach is that nowadays, because of this new neural network methods that we are experiencing right now, we can now train a neural network to represent some distribution. And this line of work is called, sometimes called deep generative models. In some area, they call it generative AI because they think it sounds more fancy. So essentially what we are trying to do from deep generative model is that we are trying to train a neural network given a training data. We are trying to train this model to estimate the distributional properties. So for example, we are trying to estimate the likelihood of the data sample, or sometimes that's sometimes too hard. So we are trying to generate samples that has those realistic distributional properties that were in the training data. Okay, so this talk, I'm going to focus on 3 different things. So first one is my PhD work where I focused on the generation part of the generative model. And the second part is the density estimation for estimating the likelihood directly from the data. And then third part, I'm going to talk about some applications that I've been working on of using large language models and vision language model, which are another type of generative models trained on text and images, so that we can use it for transportation systems. So first of all, this is the type of data I was very interested in doing my PhD. So we called it urban trajectories. So for example, here we have a trajectory from Brisbane, Australia. So from this data only, we can already find a lot of information about this trip. So we have the origin destination information. Sometimes we have the routing information. And for some type of data, we have the speed contour of how the speed dynamics work during this trip. What's more interesting is when we collect a massive amount of this trajectory data, then this full data set kind of represent the urban mobility pattern of the city. So for example, this video here shows the daily, so it's a traffic flow pattern of Brisbane, Australia. We can see, depending on which time of day, where the OD flow or regional flow happens, and then we can see where it's more crowded and so on. So by generating this type of data, we can do a lot of different planning decisions and also real-time traffic operations. And when we think about generating this type of data, I kind of mentioned it during my introduction. So we've been doing this type of task for many years, but so until now, or until recently, we didn't really have the observed true trajectory. So we relied on some mathematical assumptions of trip generation, route choice, and mode choice, and then using some behavior model to simulate. And then we hope that the simulated trajectories are matching the unobserved true trajectories based on some measures like aggregated traffic flow. However, there are some limitations such as complex model building and calibration process. So if you have ever done some kind of calibration, you know that there's so many dependencies, so it's taking a lot of headache. And then sometimes we rely on strong behavioral assumption, and sometimes we rely on very simplified physical process, such as approximating into first order equation. But what if we have almost infinite number of data points and then almost infinite computing resources? And we are kind of experiencing that type of era right now, because we've seen many generative AI models like ChatGPT, which are trained on almost infinite number of text data and almost infinite number of trillions of dollars of computing resources. Then we can approach this problem differently. And actually, we are approaching that era because we have the connectivity, connected automated vehicles, and Internet of Things, which will generate, say, more than 100 gigabytes of data from one device every day. Okay. Now, because we have this actual observed trajectory, now what if we can use data-driven and learning-based approach to model the distribution of the trajectory and then sample from it so that we can get the generated trajectories directly from this learned distribution. It's going to rely on less behavioral assumption, and then it's going to make us understand this complex spatial temporal dynamics of traffic flow. So that's what I've done for my PhD, and I'll just give a high-level overview of how I did it. So previously, this type of model relied on some recurrent neural networks, and then typically what they would do is that they will predict next location step by step, but kind of intuitively, this has a limitation that if some error occurs on the way, the error will be accumulated so that the whole trajectory will not make sense. So the approach I was taking is that we want to incorporate the distribution of future trajectories. So we used generative adversarial imitation learning, which is a type of generative model. And then we combined it with recurrent neural networks so that we can use that distributional characteristics in predicting the next location of this of the trajectory. So I'm not going to go into the details, but essentially we are using two neural networks competing each other to generate realistic trajectory. And in terms of generating, so if we are generating individual trajectory, then we want that trajectory to be realistic. And also when we are sampling, say, millions of or 100 millions of trajectories out of this generative AI, then we want the aggregated behavior to be matching with the realistic real-world characteristic. So we use two different methods two different ways to evaluate the model. And because it got published, so our model performed the best among the state-of-the-art models, especially for the real-world data set. We gained more than 6%, up to 23% of improvement with less standard deviation so meaning that we were more stable in generating realistic trajectories. And also in the aggregated level or data set evaluation, it was shown that it's more robust to increase of the complexity of data set. Okay. Then I kind of moved on to other types of trajectories. So nowadays I'm more interested in looking at microscopic trajectory data. For example, pedestrian, cyclists, sometimes airplanes, sometimes vehicles. And what I want to do is essentially say if we have some historical location of some agent, say pedestrian, we want to predict the future trajectory of this agent. And what other people have done so far is that they design very complex neural network to predict deterministic trajectory. But that's not going to happen especially for the pedestrian. We know that they are so uncertain that it's almost very hard to predict. So it's going to be some form of distribution. So we are now trying to learn the distribution of future trajectory given past trajectory. And for this specific task, I'm using a method called normalizing flow. So essentially, we are learning the transformation function from a simple distribution to a complex distribution. And there's this very nice mathematical property that this gives the exact likelihood of the data sample, meaning that if we can sample something, we know how likely that sample is. So for example, if we are applying it to pedestrian, we can know at which time step, at which location, how likely it is for this vehicle or pedestrian to be at that location. So this visualization shows the likelihood of future trajectories. And then if we have this type of model, we can use it for intersections monitoring system, also kind of doing some behavior analysis on interactions between the agents. Also, we are using airplane trajectories. So for example, here we are predicting trajectories of surrounding aircraft, conventional aircraft, so that we can use that information to plan the routes for the UAM, the air taxi, eVTOL, so that it can pass through this uncertain airspace between this airport to the Seoul city center. So this is the illustration of how we kind of designed our prediction model, and then how we use that information to plan the green dots here, which is going to avoid the crash between the red one, which is the conventional aircraft. So I kind of talked like there's so many new brilliant thing about this, but there's also some limitations that has to be addressed. So one of the things is the scalability. So when we are dealing with a large high dimensional data or external factors that we want to consider into the modeling, then the model kind of blows up, and then usually it increases the number of parameters by quadratically to the number of input we have. So we have the curse of dimensionality. Also, in terms of generalization, typically these models only work on in-distribution cases. So making it to work for out-of-distribution cases so that we can do some what-if analysis, it's going to be very challenging. So that's one of the topics that I'm working on right now. And one of the directions I'm working on is to make the model learn the causality behind the data generating process so that the model understands what made this data happen. And if you're interested in this line of direction, we recently got accepted in CR2C on a survey paper, review paper on applications of the generative models in transportation research. So if you want to read the paper, I have to warn you, this is the original version was 68 pages. After revision, it's like 80 pages. But we have the code, starting code, including some tutorial materials of generating speed contours and house survey data. So you can start working on and experiencing what these models can do. I think I'm doing good.
2 minutes. Yeah.
Okay. So nowadays, because this really big trend of using large language models and visual language models, I'm also doing some research related to this. So essentially, large language models, visual language models like ChatGPT is not something brilliant, but it's more like a generative model that we just talked about, but they are trained on large amount of text data and image data. And because they have the ability to understand the natural language and they understand the images or the visual scenes, we can build some agentic AI that understands the both visual and text input. So maybe this will have the ability, I'm not sure if it has now, but it'll have the ability to perceive and reason and act like human in the future. And then it can, if it can do that, it can work as an interface between human and machine or human and AI. So that's one of the things I want to do. So one of the application scenario I'm kind of dreaming and I'm working on right now is to build a TMC agent, so Transportation Management Center agent. So for example, we are using some traffic data, video stream data to understand what's going on the traffic scene. So that's the typical job of this person right here, looking at the video streams from the management TMC. But then maybe we can use traffic simulator to find, or maybe we can let the AI to find optimal solutions through traffic simulator as if we are doing in our research work. And then suggesting that control logic back to the operator so that they can use both AI-driven control logic, plus they have some reasons why this is good. Also, we are doing some research on using visual language model for driver assistance and autonomous driving planning. So for example, this video here will show some text where it's kind of showing how it's understanding the scene right now. We are using recent data for this one. So if it sees some obstacles or it sees some truck stop nearby, it's going to alert the driver on this, and then it's going to plan what kind of actions it has to take or the driver has to take depending on the circumstances. And we can even imagine having a visual language model, multiple visual language models driving in the urban scenario, kind of talking to each other in natural language. So they're talking in natural language to kind of navigate through the intersection. Also, we can imagine having one human driver with visual language model autonomous driving, talking to each other to navigate through intersections as if humans do between each other. So that's it. Thank you so much.
Thanks.
Yeah, I wasn't too.
No, that's amazing. Okay, so again, thanks everyone for your patience here. So we now have our last speaker, Dr. Ali Raza Khani. He's an associate professor in the Department of Civil Engineering at University of Minnesota. His work encompasses multimodal transportation systems, broadly focusing on transit vehicles as well as electric vehicles and integration with freight. He has led projects on transit accessibility funded by NSF, Federal Transit Administration, and his background includes PhD in transport engineering at University of Arizona and a postdoc at UT Austin. And he also holds a joint affiliation with Industrial and Systems Engineering at UM.
Thank you very much,
Appreciate it.
Mantesh. Everyone is ready to go home. Bad news, the bus is scheduled to come in 15 minutes. It may come in 25 minutes. But yes, I'm gonna talk about transit, and I'm gonna start with this graph that shows the transit ridership in the last 100 years in the US. Starting with 1920, where the population of when the population of the United States was 1/3 of what it is now. We had the rail system that was the dominant mode of transportation, and then it was gradually replaced by buses, but they could not sustain ridership, and then ridership declined until now. And here, can we move this a little bit?
I think it's on your screen. You can just move your finger.
Yeah, okay, cool. No, it's okay. Even here in the 2010, ridership has been declining due to affordability of cars, lower gas prices, and so on. And guess what? COVID-19 happens. And it impacts the even decreasing ridership trend in the US. And if we look at one particular example, the Minneapolis, St. Paul region, ridership has been declining by about 60%. Oops, sorry. 60% for different modes of transportation, for rail system, for buses, and so on. So this is the situation in most, if not all, the transit systems in the United States. Maybe New York City is different, but most of the mid-sized cities are dealing with the same problem. And the ridership has not been back to the pre-COVID era. And then in the rural transit, situation is a little bit different. In rural transit, we have both fixed route scheduled buses and also dial-a-ride system or demand responsive systems. Demand responsive system is actually showing a rebound of the ridership. Why is that? Because this is what people need. People who use transit, they rely on it for everyday work, for working, commute trips, for medical facilities, for educational trips, and so on. So they don't have other options. So that's why the ridership comes back. For fixed route, it's a little bit different, similar to the urban system. So in general, transit is dealing with the difficulties nowadays for many different reasons. And most of the reason is the limited service of transit, both especially and temporary, the low frequency of buses and not the great geographic coverage of the buses. And the issues of safety and security is a layer on top of that after the pandemic. There are issues with, homeless people taking transit, and crime rate, at least the perceived crime rate, has been increasing. So transit is in a situation, and the question is, how can we use technologies to improve transit, to supplement the existing transit systems with mobility on demand system, with mobility as a service platform, and so on. In rural transit, as I mentioned, there are fixed route buses, and there are demand responsive buses, and there are route deviation, which is kind of the fixed route buses, but can deviate up to 3 blocks upon the request of the riders. In Minnesota, in rural area, in Minnesota, we have the Twin Cities region, but the rest of the system is, the rest of the state is almost rural, with the exception of a couple of larger towns. There are so many different transit systems that operate in rural areas. For the users, for the residents, it's really difficult to use this system. Sometimes they don't know about the system. Okay, what service is available in my region? And then how to make a reservation, how to make payment, and so on. A couple of years ago, Minnesota Department of Transportation implemented a mobility as a service platform in the southeast region of the state using the transit app. The MOS platform tries to integrate all the information from different service providers and allow trip planning and reservation. And at the time during the project, it was up to reservation, and then booking happened after that. And we were a research partner with this big team of consultants, technology vendors, and DOT. And our goal was to evaluate the system performance and whether it helped the system gain ridership. We use time series analysis. I'm skipping all the equations and the method, and here's the result. This is showing the ridership over the 1 year, including the before deployment and after deployment, for the target group and the control group. the target group showed after each feature of the bus is deployed, there's a jump in the ridership, but then there's regression to the mean. Comparing with the control group, we see similar behavior, but actually, if we do SARIMA modeling, this is an autoregressive integrated moving average, I'm sure many of you are familiar with that, we concluded that the mouse actually led to 4% ridership increase in a very short period. Well, the question is how to sustain that ridership gain, but that's kind of the end of the project that we had, and that we are working on continuation of that project in different aspects. There are other parts of the study that led to the conclusion that it actually removed a lot of barriers to people who would otherwise not use transit, anything from language barriers, payment methods, and many different things that prohibited them or made it really difficult for them to use transit. The MOS system made everything available to them using through the smartphone app. Another thing is that the dial-a-ride system is reservation-based. It's you call and ask for a service at 8 a.m. tomorrow. And if the system is at saturation rate, sometimes you cannot be accommodated. And the operator would ask you, well, can you make the trip at 8:30? And that 30-minute difference is the scheduled displacement. The real data showed that a significant portion of users experience a large scheduled displacement, more than 30 minutes. And this is because a lot of people who live near bus stops, they don't use the bus. They use the dial-a-ride system or demand responsive system because it's more convenient and not much more expensive. It's pretty much the same fare. So we propose, and that's about 40% of the riders who can be served by buses, but they're using the demand responsive system. So we propose a platform in which people can be given two options to choose from. The earliest arrival is most likely the curb-to-curb demand responsive system that can serve you. You get to your destination as fast as possible for a fair amount. Or if you are, if you can be served by a combination of demand responsive transit and fixed route service, the system will calculate the routing, optimal routing, and assign you to a multimodal tree that helps the system. And then you save on the fare as well, you save some money. We did some simulation to see how it really helps the system. As the participation of the user in the flexible option increases, we see that there is a decline in scheduled displacement, both for those who opt for the flexible option and for those who did not opt for the flexible option. The in-vehicle travel time of these people did not actually change, even decrease for one group of people. And importantly, the operating VMT, vehicle miles travel in the system, decreased up to about near 10%. So in general, it's great saving because people can save time, both on the scheduled displacement, a little bit in vehicle time, and the system can reduce their operating costs and all the externalities of the additional vehicle mileage. But I mentioned that one of the issues with reduced transit ridership is lack of access to transit systems, especially in auto-oriented areas in low density land use. People more likely opt for owning the car and using their own personal car for their trips. And it makes the transit even less attractive. And because people have to walk from the bus stop to their final destination, they have to cross the streets or walk in large parking lots, it becomes inconvenient and even more people opt out of transit. The question is that how can we use technology to address this issue? And particularly here, we are looking at the physical technology. The previous one was more like cyber technology. But here, we are looking at mobility on demand systems, pretty much similar to what Michael talked about, mobility on demand system with autonomous vehicles in which users can request a ride through their smartphone, get picked up, dropped off at their destination. But the key point here is that we want it to be integrated with the scheduled bus services. We want people to be picked up as soon as they get off the bus and be transported to their destination. Or if they want to go to the bus stop, the dispatching will be synchronized with the bus schedule so that when you get to the bus schedule, the bus is waiting for you to get on. So we use the linear dynamical system with state variables being the number of vehicles and number of passengers in each zone. And the control variables are the customer carrying vehicle dispatching and rebalancing of the empty vehicles. I have probably only one slide with the equation, and that's this one, some propositions. There's infinite number of equilibrium points if we have a network of more than 2 nodes. And more importantly, the equilibrium can be obtained by this system of equations. The number of customer carrying dispatching should be equal to our demand. And then the rebalancing can be calculated from the system of equations, with E being the incidence matrix of the graph and lambda being the demand, the stochastic demand, or the mean value for the stochastic demand. 2 corollaries, I mean, I mentioned about the infinite number of equilibrium points, but this one is really interesting. If demand satisfies this equation, rebalancing is not required. Imagine a mobility on demand system with symmetric demand, right? We don't need rebalancing. But that's a very strong assumption and condition that doesn't really happen in reality. But this one indicates that even if the demand is asymmetric, there may be conditions that rebalancing is not required. This is a highly asymmetric demand, but it's self-rebalancing. This is also asymmetric, but it requires rebalancing in that one, because we need to bring the empty vehicle back to where the origin of the trips are. And then for solving this linear model, first we need to find the equilibrium point, the desired equilibrium point. That can be decided by the operator. It can be the cost as a function of rebalancing scheme, subject to all the equilibrium conditions. And then after finding the desired equilibrium, we can regulate the system around that equilibrium point with, for example, MPC here. We applied it to, I think I'm going to skip this slide and show this one. This is a case study in Duluth, Minnesota. This is a large shopping area with Costco, Walmart, and shopping mall, and many other stores. There are buses that bring people here from the residential part of the town, but actually they're not efficient. They're zigzagging through the store, parking lots, etc. And people who get off the bus, they still need to cross the streets, go through parking lots to get to their destination. And our goal is to develop this autonomous mobility on demand system that can be integrated with the bus system to transport passengers at the doorstep of their stores, at their destination, basically. We develop this learning system and so on. The end goal is to have this integrated system such that people from their origin, from their home, for example, can take transit, go to the near the shopping area, the transit hub, and then use AMOD to get to their destination. And by doing simulation and demand modeling and so on, we want to know how much transit can be demand can be attracted to transit. And here is some results. First of all, the AMOD system itself has a great performance with the algorithm. The waiting time of users is on average for different scenarios, different fleet sizes, is 2 minutes or less. The queue length is, of course, correlated, and that's less than 1% at a time at each station. The number of customer carrying vehicles in the system is linearly increasing. And do you know why? Because people are being attracted to transit. There is more demand for the transit system. People are getting out of their cars and using transit to travel to this location. And therefore, at the end of the day, we need to serve these people. Therefore, the customer carrying vehicles are equal to the transit demand. But in terms of rebalancing, which is a measure of cost in the system, there's a little bit of increase in rebalancing of the vehicles, but not significant compared to the customer carrying. And again, the last point, last but not least, there is VMT saving in the system as we add more fleet to the system, more people use transit, and then we have net VNT saving in the system. So I guess I'm going to stop here. I have some remarks that I'm going to skip. This is more about my philosophy about transit, the fact that we need high frequency, high capacity, reliable fixed route service in urban area and busy area, but we need supplementary services such as autonomous mobility on demand system to serve these core routes and bring people and provide accessibility to the basically covering the last mile access issue. Acknowledgement of my sponsors, collaborators, and my wonderful PhD students, Konko and Ali. Thank you very much for your attention. I'm happy to take questions.
Wonderful. Thanks to all the speakers for their great insights. I think they were over a spanning number of topics, so we can now move on to questions. And if anyone in the audience, first in person, and then we can move to the virtual world if there are any. So questions for any of the speakers, and
I have one question about the generative AI. Have you noticed that the AI models have been able to comprehend spatial awareness? Like for instance, you have the predictive movement as well as the intersection, but have you noticed any type of errors or confusion with spatial awareness of like where it is with respect to each other?
So are you talking about the intersection? And I'm sorry to interrupt. If the speakers can go forward so that the cyber side can hear you. So are you talking about the intersection?
Yeah.
So in that case, we are using data from that site. So kind of that spatial information is kind of embedded inside the data distribution itself.
Yeah.
So, but we are not really constraining anything from the modeling perspective, but more like the model learns by itself how to like kind of consider like where is a feasible location for this vehicle to be or pedestrian to be, while this place is not. But the spatial awareness, I think it's also very hot topic in vision language model work, especially for autonomous driving. And so far, my experience is that the state-of-the-art vision language model still doesn't have the spatial awareness. But I think as we progress further, it might have some sort of spatial reasoning capability or spatial awareness in the future.
And then part two, you had that future work where you're talking about like collaborative intersections.
Yep.
So you have like a large language model there. Again, I'm asking, does it really understand spatial awareness of like where it is with respect to the other person?
So for that specific scenario, we are trying it in Carla environment.
Yeah.
In that scenario, we are getting some good result. We are not, so we cannot really look into their mind.
Yeah.
See if they actually have that spatial awareness. But based on our experimental result, we think that they have a good understanding what this scenario is. And then if we can further fine tune the model, now we are using almost zero shot or in context prompting to make this type of spatial awareness happen or make the BLM understand what autonomous driving is.
Yeah.
But then if we can further fine tune using say reinforcement learning using human feedback or something like that to further train the vision language model to have that spatial awareness, I think it's possible. It's not present, but it's one of the features.
So I was looking at that and I was thinking about like, okay, well, what if you had same scenario, but for like merging?
Mm-hmm.
So you have maybe visual AI helping figure out when to merge, because if you had an autonomous car, they're all going to try to merge the same spot, like say like 1 mile out, try to merge in, and then you're going to have a traffic jam there. So I'm thinking, well, what if you had like an AI level on top of it to find a weave to understand the state of the traffic and then try to
kind of distribute
of
lane changes.
Yeah.
That's like having like a upper level AI that kind of controls all the AI and then have other AIs kind of responding to that.
But in my mind, I think that would be easier than me trying to make an algorithm to do that, because it gets very complex.
Yeah, but those so it's like a trade-off, I think.
Yeah.
So when we try to build those type of centralized system, we have to think about when it gets, say, all the vehicles, say, 2,000 vehicles per hour, are all autonomous vehicles, and we have to handle that type of situation through one single AI, it's going to be very inefficient, where we have decentralized AI agents, which can almost handle, say, 95% or 99% of the.
Because I was thinking, you put a model on the car and then say, give it the surrounding scene and let it understand when to merge in based on its current situation.
Yeah.
And everyone kind of has their own brain.
Yeah, and then, but then we can kind of separate the tasks, like the upper level AI can do more like a, or long-term planning of kind of deciding the distribution of the lane change spots, and then giving that information to the decentral, like the lower level AI to decide whether it should kind of merge now or it should wait until it reaches to the actual merging.
And then one last question, going back to the pedestrian, what kind of data did you collect to track that?
That is an open source data that's called Indeed. That they have a variety of different data from roundabouts, intersection, highway. So we use intersection version of it.
Yeah.
So it's
The camera database or is
it's
it
drone based.
drone based?
Drone based. They have coordinates every 0.04 seconds, so 25 hertz of data collection. They have XY location, and we use 4 seconds, so 100 input, 100 points as input, and the next 100 as our target range.
Okay, thank you.
Great, thanks. Any other questions about the speaker?
Yeah, go ahead. What's going on?
Yeah.
And if you can get closer to the
The mic,
line,
mic.
that part louder.
So I had this question, like I really like your model of multimodal transit system that you explained. So I was thinking that how successful that model will be, say, for example, in Appalachia region or rural areas where we do know that, transit is an issue. So how do you see like solving issues for the rural or the Appalachia region in terms of multimodal transit systems?
Thank you very much for the question. So that model was actually in a smaller town of Duluth, Minnesota. How big is maybe 200,000 residents? Okay, it's definitely a small town. It has some fixed route transit system. And actually, we had this conversation with the transit provider in the region, and they said, well, actually, our transit system is quite good in terms of the coverage of the different parts of the region, but it's not great in terms of the frequency. So there may be gap between the bus arrival interval, and like every 30 minutes there may be a bus. So this is kind of a mix of urban rural area, and that's exactly what we wanted to pick for an area that has some transit, but it can be, there's potential for complementary service to that system. If it's a rural area that there is no transit, that's a different story. But I'm not sure if I'm really answering your question, but the goal is actually to serve areas that there is some transit, but this is not like urban transit. This is basically developed for them. I'm not sure if I answered your question. Do you want to ask a follow-up, maybe?
Yeah, like the follow-up question I just had this is that maybe what different modes that you're considering like to connect it with transit, or like what could be the potential modes like when we are connecting like
Oh, okay. So this autonomous mobility on demand system, or maybe a different terminology, maybe a micro transit. This is one option, and many of these are actually happening organically by different transit agencies. Locally, they provide this service as the technology is developing. Other systems, maybe bike sharing or scooter sharing and so on, that can also supplement transit. Unfortunately, for some years, these systems emerged and they actually took some ridership from transit. People who were using transit, now for short trips, they're using bike share system or scooters. So it has been competing with transit. But the opportunity here is to actually complement transit rather than to compete with transit. So in terms of modes, yes, there can be different types of modes like bikes, scooters, microtransit like this. But the key point is that there has not been much studies on really evaluating the system, how it competes or complements transit, and how actually we can integrate it with the transit. So this is kind of one study that shows the potential rather than the harm to the transit. Yeah, it can be expanded definitely to different technologies.
How do you think of getting the data for this,
Yes, I can try to make it quick. So the data, the demand data that we use is actually from the Metropolitan Planning Organization in the region. Cell phone-based data, we had the origin destination from different parts of the town. The missing part in this study, given the time and budget, was the people's perception of autonomous vehicles, because people may not feel comfortable being an autonomous vehicle, general public, or they may get excited. So how would you perceive 10 minutes in an autonomous vehicle compared to 10 minutes on bus or 10 minutes in your personal vehicle? That's a parameter that unfortunately we didn't have any data for. This is only a simulation, but we had a conversation this morning that maybe we can do some collaboration, get some perception parameters calibrated from real data. Thank you.
You have one
One question online, so I guess we can move on to that. Do you want me to read it?
It says, in some distant future, when autonomous vehicles have achieved complete market saturation and are ubiquitous as human-operated vehicles are today, do you foresee the necessity of a complete infrastructure revamp to maximize efficiency, roads, highways, access ramps, etc.? Or do you instead predict an en masse repurposing of existing infrastructure?
I'll start. I think Michael has some work that he's done on this. Not to put you on the spot, but I mean, like stuff like AIM, right? Autonomous intersection management, where you can, I think it's, I mean, from my perspective, my hope is repurpose. We spent billions of dollars, right? I mean, trends will change, I think. And this is sort of like, if you lower the cost, what you're doing is you're lowering the cost of travel, right? Time is money, and you're kind of removing the time aspect. We've all gotten used to like work from home. Why not work from car? Right? Why not commute for 2 hours or an hour and a half, right? And start your Zoom meetings, et cetera, from your car. If you're not driving, you could make it a nice, comfortable office, do a Zoom call, show up for a few hours of meetings, and you could see a huge increase in vehicle miles traveled, potentially. And so that might mean that our current infrastructure just isn't enough. But my hope is repurpose. And there's ways that, so for example, I know Michael's done some work on like autonomous intersection management, where you say, okay, if we're actually in a, autonomy is ubiquitous and we have connectivity, then things like traffic signals might become less necessary, because you can just tell the cars when to go and when not to go. And in some settings, you could have them all go at the same time because they can coordinate. And there's some nice stuff there, but I think at the end of the day, if we're still talking surface transportation, hopefully we can take the existing infrastructure and repurpose it somehow. I don't know. If anyone else has something they want to add to that?
There are a lot of new traffic control codes around in vehicles. So it's the physical infrastructure that we're involved in working with, because that's very expensive. But the things like traffic signals or other controls, you can redesign them. You don't necessarily need green lights or red lights, for example, and talk to automated vehicles.
And the one thing, I think that the biggest factor here, which is the part that I hate talking about, is the human behavior part, right? As an engineer, I really want to not consider that, because, but I have to, you have to. And that's the biggest, I mean, these are very, I think just like the choice, the route choice you make is a very personal human thing. Do I not like being on the bus because I don't want to have to say hi to other people, right? That's acceptable. Some people don't like being on the bus or the train because they don't want to interact with other people. They don't want to have to buy fare from somewhere. They want to be in their own space. These are really, really like personal human things. There's one study that I'm aware of that like tried to get at like how will people's behavior change with automation. Joan Walker, UC Berkeley, some of you might have seen this before, did a study where she was sort of like We don't have automated vehicles en masse yet. But what we can do is the next best thing is hire a chauffeur, right? So you still have to drive. It's not that you can get rid of the car. You're still sitting in the car, just you're not responsible for the driving part of that. You can tell the chauffeur to take you wherever. So they track people's travel behavior, like I think it was a week or two without a chauffeur, then a week or two with a chauffeur, and then again a week or two afterwards. And across the board, unsurprisingly, people's travel behavior increased. They were still paying, it was their own personal car. So they were still paying for gas, they were still paying for mileage. They just didn't have to do the task of driving. And there were two things that they saw. So the first one was the group of people, the population that saw the biggest increase in driving. I've heard a lot of like, oh, you know, young people don't like to drive. They don't care, they like to drive. It's retirees. They saw a huge increase, and a large part of it was retirees driving more in the evening once it's dark. And like retirees being able to be independent longer and meet up with friends for dinner and feel comfortable going home is a great thing, right? That means that's economic activity. It's solved, you know, it's addressing our loneliness, right? Like loneliness of older people. It's a really good thing. But if you're a traffic engineer, it means potentially, you know, 20-30% more trips. And so I think the bigger, my guess is the bigger from an infrastructure perspective, it's gonna be more a capacity thing. So hopefully with connectivity, that will resolve some of that. But those are, I don't know. I'm curious if other people have different thoughts, because I'm not, we've gone beyond what I'm an expert on.
I also hope that autonomous vehicles don't take trips from transit. We do need transit. Imagine a place like Manhattan. How can we really serve this demand?
Even with full connectivity, full everything.
Yeah, even 4 people in a car, no, we can't do that. We need subway, we need buses. But AVs can connect.
The best we can do, if you think about like 2,000 vehicles per hour per person, right? Okay, let's say we cram 5 people into a car. People do not like Uber offered it for years. They offered pool and they got rid of it because people didn't like it. People don't like it. People don't want to share their car. They want their own car. But let's say we do that and you use connectivity, so you double the capacity. We're talking 4 times 5 is, what is that, like 20,000 people per hour per lane? And I think a rail line still does better.
60,000 New York subways.
Exactly.
Capacity.
Exactly. So that is, what is that? A factor of, what did I say? 20, a factor of 3, right? So.
Yeah, I think since we are at time, so we'll end up the
Yeah,
Q&A
exactly.
part, and our speakers will hang around. So thanks again for everyone for taking your time on Friday evening, and everyone online who joined us. And let's do one round of applause for our speakers again.
Exactly.